Hi, myself Dr. E. Sridevi, Professor Department of Electronics and Communication Engineering. In this video lecture, we are going to learn about Ampere's law. On completion of this, the learners can be able to understand Ampere's circuital law, understand the applications of this law, and solve the basic problem based upon this law. So this Ampere's circuital law states that magnetic field produced by electric current is directly proportional to the intensity of the electric current, and the constant of probability here is the permeability of free space. That is, the statement of Ampere's circuital law is closed integral B dot dl is equal to mu naught into I enclosed. The magnetic field around the wire depends on how much current flows through it. This is the magnetic field and small element. It is useful for highly symmetric structures and long straight wire solenoid toroid infinite sheet of current. It gives the magnetic field quickly without complex integration. The application is it transforms used in transformers, magnetic energy storage, inductors in power electronics. So the magnetic field around this wire, current carrying wire, is noted as B dot 2 pi r equal to mu naught into I. From that, B equal to mu naught I divided by 2 pi r. I is the current and r is the distance from the wire. Here Maxwell's equations, according to Maxwell's equation, del cross H is equal to J plus dou D by dou T. So the following image here, H dot dl is equal to I into enclosed. This is the equation of Ampere's law. Suppose the current carrying conductor with current I, then this current generates the magnetic field that surrounds the wire. So the formula for Ampere's law is equal to the line integral of the magnetic field around the closed loop, such that it equals the number of times the algebraic sum of current is passing through the loop. So simply we can tell that B dot dl equal to mu naught into I, where mu naught is the permeability of free space and I is the current. So B dot dl equal to line integral of B around the closed path. Notations used in this formula is mu naught is the permeability constant with the value of 4 pi into 10 power minus 7 Newton per ampere square, and B is the magnetic field, and I is the flow of current passing through the closed loop, and L is the length of loop. For the closed wire, the value of I is 2 pi r. So the value of magnetic field intensity is given as B equal to mu naught I by 2 pi r. Determining magnetic field by Ampere's law, the magnetic field at r distance from the wire is calculated by using Ampere's law. For wire conducting I current, the magnetic field at the distance r is calculated using Ampere's law, and its direction is given using right hand thumb rule. Applications of Ampere's law. It is used to calculate the magnetic field produced by the current carrying wire. Ampere's law gives the magnetic field inside the toroid. Ampere's law gives the magnetic field inside the conductor. It also provides ways to calculate the force between two conductors. So we have one simple example. Based upon this, find the magnetic field of a closed wire with a radius around 0.2 meter if a current of 2 amps is flowing through it. Solution is, so it is given data r equal to 0.2 meter and I equal to 2 amps and mu naught equal to 4 pi into 10 power minus 7. And here, as per the derivation, we know B equal to mu naught I by 2 pi r, and here we are asked to calculate what is B. So substituting mu naught I and r values here. So 4 pi into 10 power minus 7 into 2 into 1.25, it values is equal to 2.011 into 10 power minus 6 Tesla. And another one problem, for a long straight wire carrying 5 amps current, find the magnetic field at 0.1 meter from the wire. So B is asked to calculate, and B is equal to mu naught I by 2 pi r. Substituting the value of r, mu naught I here, so 4 pi into 10 power minus 7, that is mu naught value I equal to 5 amps, so into 5 divided by 2 into pi into r is equal to 0.1. Substituting the value is noted as B is equal to 1 into 10 power minus 5 Tesla. Thank you for watching.